Bismillahirrahmanirrahim. Assalamu alaikum everyone. So in this lecture we will continue the discussion that we had began about a week ago, in fact 2 weeks ago, about the inverter circuits. We'll continue that discussion. In the first lecture we had just the introduction of inverter, the third category of power electronic converters that we are discussing in this lectures. In the introduction we had discussed generally about what the inversion is. Then we had also briefly discussed about the two broad categories of inverters, that is voltage source inverters and current source inverters. And then further we had discussed the categorization of voltage source inverters. We had mentioned that it is having three general types. The voltage source inverters can be categorized as PWM inverters. Then we had mentioned about the square wave type inverters. And then there was a third category, not very common, but of course it does have some limited applications, that is single phase inverters. With voltage cancellation. We had described the differences among these three types, and in fact this has this prefix of single phase inverter with voltage cancellation, because this type is only possible in VSIs in the case of single phase inverters. It is not possible, or it does not exist in the case of three phase inverters, okay, while the other two are possible for both of them. And furthermore, in fact, the square wave type of inverter is one subcategory of PWM inverters. How is that? We'll see that in this lecture. Okay, today then in the second lecture we had discussed about the edge bridge type of inverters, or the type of inverters in which we do have the square wave output. Okay, we did not discuss that how does the switching of the power electronic switches that are involved in the inverters are being switched, okay, and that helps us get a certain waveform, normally of square wave type, at the output. So in this lecture we'll also develop some concepts and understanding the relevant terms and definitions of the switching methodology involved, okay. That will help us give an idea that how the switching action is performed, what are the input signals that are being applied to the switches, okay, and if you want to get a signal of one particular frequency or magnitude, so how can we control the switches, or what type of signals we can apply to the switches to get those outputs. In the last lecture, in which we had discussed about the half bridge and the full bridge inverter circuit, in which we had like a pair of switches, or in the case of full bridge inverter we had two pair of switches which were being switched simultaneously or pairwise, okay. But in that we did not focus on that how the switching is actually taking place, okay. We just mentioned that, okay, if this pair of switch is turned on and the other one is off, and vice versa, or in the case of half bridge inverter, if one switch is turned on and the other one is kept off, and vice versa, so what will be our output, okay. So it was made to look very simple. In this today's lecture, after developing the understanding of the relevant terminologies, we'll see that how does this switching actually take place, okay. What pattern of signals the control and carrier or reference is being applied, and that basically makes this process work in you can say in an automated way to get the desired signal at the output, okay. So that is what we are having our intention to cover in this lecture of the inverter circuits, okay. So coming back to some of the basic circuits, okay. some of the basic concepts related to this inverter circuit. Let us generally have the block diagram representation of a single phase inverter circuit, in which we, let us say, that have a certain topology of inverter, in which we just idealize it that we are having some capacitor on the input side. Okay, we have got some certain signal on the input side. Okay, and we say or assume that this is a single phase inverter, and plus it does have some filter at the output as well, so that we can get a clean or the desired signal which we want to have at the output side. Okay, normally our requirement, our desire is to get a sinusoidal wave at the output from the inverter circuits. Okay, so let us say that this inverter circuit is not only performing the inversion function properly, but also, since it does have a filter component as well, so we assume that it is giving us a proper sinusoidal voltage at the output. So let us say that this is the voltage signal that we are getting from this particular single phase inverter, which does have a filter at the output as well. Okay, now further we have already had this discussion in our last lecture, that if our load is simple resistance or is of resistive type, so in that case like the voltage and the current waveforms at the output will be perfectly in phase with each other. But let's become a bit more realistic over here in this case, and let us say that we do have some practical load, for example an AC motor, in which we will have, of course, a significant portion as inductive. Okay, so it will be an RL type of load, not purely resistive load. It will be like inductive for a significant portion, or a combination of resistance and inductance. Okay, so this inductive load will mean that the output current, that is I naught over here, lags V naught by some particular phase angle, let us say that is phi. Okay, so if you want to plot the current waveform, so we'll have something like this, for example, that will have a certain lag, and it will start after this 5 degrees. Let me try and redraw it to be. If we further extend it over here, okay, so this is my current waveform, that is I naught. That is because of the inductive load or a practical AC motor that we have, that it will have some certain lag with respect to the output voltage waveforms. Okay, and if we just have a close examination of these two waveforms or comparison, we can say that we have different subintervals. Okay, and how do we have these subintervals? Basically, these subintervals represent the combination of polarities that the output signals are having during these intervals. Okay, how is that? Let me mark them, and that will make it a bit more clear. Okay, now we can see that these different subintervals are labeled, or these boundaries are drawn with respect to the similarity or the difference of the polarity in the output voltage and current. Now here you can see in the subinterval 1 the output voltage is positive. Okay, but the output current is negative. Okay, in this subinterval, which is the next one, okay, we can see over here that the output current is also positive and the output voltage is also positive. So this is another subinterval which I have labeled as 2. In the third subinterval, we can see that although the output current is positive, but here you can see the output voltage is negative. So this is another subinterval, and then beyond this beyond this boundary in this subinterval, we can see that the output current is negative and the output voltage is also negative. Okay, so if overall, if we look at the power flow, okay, or if you want to calculate the power flow direction, okay, so the instantaneous value of power will be of course equal to the product of voltage and current. Okay, from the introductory circuit analysis courses, you all might have this understanding, okay, that if you want to determine whether power is being absorbed by a certain circuit element or it is being delivered by a certain circuit element, so that it is determined with the help of passive sign convention. If the product of instantaneous voltage and current comes out to be positive, okay, so that means, so for positive sign, it means that power is being absorbed by that particular network element, or if it is negative, so that means that power is being delivered by that particular network element. Here in this case, since our intention is to transfer the power from the DC side of the system or the network to the AC side, and that is how this circuit will work in the inverter mode. Okay, so here what is happening that whenever we do get positive sign, okay, so that will result an inverter mode of operation, and in this particular case we can see that during subinterval 2, okay, and during subinterval 4, the signs are like same. For understanding, we can say, or the overall sign of the product of voltage and current is positive, so that means that during this subinterval the power is flowing from the DC to the AC side. Okay, and this is the system or this circuit is working in the inverter mode. However, for this subinterval, okay, subinterval 1 and the subinterval 2, since the voltage and current are having opposite signs, or overall if we take the product of these two, so we can say that power will be having a negative sign. Okay, and this is the time interval in which the power flow will be from the AC side to the DC side. So for the other two subintervals, for subinterval 2 and 4, the system is said to be operating in the inverter mode. Okay, while the same system or the same circuit for the subinterval 1 and 3 is said to be working in the rectifier mode. Okay, so if we just have you can say a plot of the respective quadrants, okay, of V0 and I0, okay, this will be minus V0 and this will be minus I0. So we can see over here that during first subinterval the V0 is positive but I0 is negative. Okay, so it will be somewhere over here. During second subinterval, both the voltage and the current are positive. This is the rectifier mode of operation, this is the inverter mode of operation. During the third subinterval, then the voltage is negative but the current is positive. Okay, and this is again the rectifier mode of operation. Okay, and the final subinterval, both of them are again negatives. This is again the inverter mode of operation for this particular circuit. Okay, just as we had a case in which we had discussed about a rectifier circuit which could also operate in the inverter mode, we had mentioned that the switches over here should have the capability of allowing the current flow in the other directions. Okay, or simply in that we had described that this inverter should have the capability to operate in all four quadrants of the IV plane, that is this VI or IV plane. Okay, and this device should be having the capability of to have operation in this four quadrants. Okay, okay, so now let us begin with the basic operation or the basic you can say building block of any of the inverter circuits. We have already discussed the inverters built using this particular basic building block of the inverter. Okay, but let us quickly recall this one, okay. And we'll see that it is given a particular name, okay, which you may come across in many literatures, okay, and that is the one leg of inverter. So let us see what is it. Basically it is a combination of two switches connected in a certain arrangement. Okay, this is one of the switches, this is the other switch. This is our source or the input point, okay. Here we assume to have two equal valued capacitors, okay, and it is assumed that they are capable of having the input voltage appearing across them by exactly the same magnitude, okay. Can give any names to the switches, but if we just want to restrict ourselves to the terminologies that are used in the book, that is of Ned Mohan, it's chapter number 8 of this book, okay. So they have labeled these as plus and TA minus, okay. So these are actually the 2 points, okay. This will have the output voltage connected across them, okay, this and this one, okay. All right, this point is labeled or referred as N, this is as O, and this one as N, this point, okay. This arrangement is called one leg of a switch mode inverter, okay. This arrangement in which we can see that we have a midpoint of the DC input voltage, okay. It may not be required in all of the cases, okay, but it is used in some of the cases, and that's why it has been shown as part of this one leg of the switch mode inverter, okay. Now there is one more thing that you are already familiar with if you have seen the PowerPoint this recorded lecture, okay, in which we had discussed that if we have only resistive load available, so in that of course we don't need anything in parallel across these switches. However, in most of the practical applications we do find the load to be like inductive, just as we saw in the example a while ago, okay. So that's why we need to have some provision for the current flow when the current changes its direction and it's different from the output voltage. So for that particular case we do have anti-parallel diodes connected across all of these switches, and we have already seen that how does it work and how does the current flow take place through these anti-parallel diodes in those times when neither of the switches is on and the current still needs some path for the flow. So that is why this is also shown to be part of this one leg, okay. Okay, so now this was one of the terminologies or definitions that we needed to have the idea about, okay. Now let's jump to the more interesting one, and that is our actual topic of this lecture, that is the pulse width modulation scheme. That is also abbreviated or written in the form of PWM, okay. So in pulse width modulation scheme, basically what we do that we provide some automatic control signals to these switches, okay, to either of these switches. Okay, if you remember in the case of DC-DC converters, we used to have a certain type of, you can say, pulse or the duty cycle, which we used to call, given as an input to that particular switch. But in that particular case, we quite often used to have only a single switch in all of the converters that we had discussed. So that did not require like a relatively complicated operation as we have here in the case of pulse width modulation scheme. Okay, basically in this pulse width modulation scheme we do have a control signal. Okay, this control signal can either be constant, okay, or it can be a time varying signal. Okay, we'll see the examples of both a constant control signal or a time varying signal. In this discussion, it will be represented by V control. So this is one of the signals, and this signal is compared with a switching frequency like a repetitive signal, okay, of a particular frequency which is called the switching frequency, and this is quite often the triangular waveform. Okay, and whatever the frequency this triangular waveform is having, that is basically the switching frequency. By switching frequency, we means that this is the frequency with which these switches are switched on or switched off. Okay, so basically what we do in this particular type of modulation scheme, this pulse width modulation scheme, that we do take the comparison of the above two signal, this control signal and triangular waveform. In the discussion when we were having about the categorization of the three types or three categories of voltage source inverters, and that in the case of pulse width modulation type of inverters, we had mentioned that in this way the inverter is capable of controlling both the magnitude and the frequency of the output voltage waveform. So basically this triangular waveform, whatever the frequency this has, is the frequency of the output signal. Okay, and then the amplitude of the control signal basically has a role in determining the average DC voltage or the average value of the output voltage that we have. So this is how these variables can be used to control the magnitude and the frequency of the output signal. Okay, so in order to produce a particular type of output, okay, for example sinusoidal or any other, okay, so the shape of the control signal should be the one which we want to produce at the output. Okay, so if you want to have a sinusoidal signal at the output, so for that particular case we need to have the comparison of a sinusoidal signal with the triangular waveform. Okay, let us see a representation of that. Now we can see its comparison over here in this first figure. This one we can see, as I have mentioned, that in the PWM scheme or pulse width modulation scheme for DC-AC converter circuits, okay, we have the comparison of a triangular waveform, okay, represented by this variable, and we can see it has a certain frequency, and the same will be the frequency of the output signal that we have, or the output waveform that we have. Okay, sorry, not the output frequency, the switching frequency. Okay, and then we have another signal which we termed as the control signal. It can be a constant, as I mentioned, or it can be a time varying signal. Here it is a time varying sinusoidal signal because in this particular case we are assuming that we want to have the output to be sinusoidal. Okay, so we can see the relationship between those two over here. Okay, so now let's define a few relevant terms, and then we'll discuss these conditions which elaborate that for what particular case or scenario either of the switches that we discussed in the previous figure, okay, in which we discussed the one leg of switches, okay. So we already have determined, or we already have discussed that this triangular waveform which will be represented with this variable, that is V triangular, as we also saw in the figure or in the representation, will have a certain frequency, okay, and that is determined, or that is labeled as the switching frequency of the inverter, okay. This frequency is also termed as like either switching frequency, or this is also termed to be carrier frequency. You might be remembering some of the concept from your communication systems course, okay, and that we also have some similar terminologies, okay. You can develop an analogy among the two as well. Okay, and then we have this control signal, which in our particular case over here is this sinusoidal signal, and let us say it has a frequency which is labeled as F1, okay. And this is basically the desired frequency of the inverter output. I earlier mentioned that the frequency of the triangular wave is that of the output frequency, then I quickly corrected it. So let me make it clear once again that the frequency of the triangular wave, okay, is termed as the switching or the carrier frequency, while the frequency of the control signal is termed as the one that is desired for the output. So whatever frequency this control signal will have, that will be basically the desired frequency that we would like to have our output signal to have. And since this is that signal which modulates the switch duty ratio, okay, so this is also termed as modulating frequency. Now in this particular case, this is only our desire to have a pure sinusoid at the output. What do we mean by a pure sinusoid? By a pure sinusoid, it is meant that the output signal will contain only the fundamental component, okay, and that is whatever the frequency this carrier signal is having, that is available at the output. But this is not always the case, okay. It will not be a perfect sine wave, okay, and it will definitely contain some components at the harmonics of F1. So whatever are the harmonics of F1, okay, so they will be present in some limited amount at the output. We'll see the representation or the figures of that as well, okay. So here we have a term which is called amplitude modulation ratio. That is defined as MA, and this is basically the ratio of the peak value of the control signal to the peak value of the triangular signal, okay. Here this V control, this variable is the peak amplitude of the control signal, while this one with a hat sign is the peak amplitude of the triangular signal, okay. Here you can see that we had represented the triangular signal with V with a subscript tri, and this control or the desired output frequency signal with V control, okay. So the ratio of these two is termed as the amplitude modulation ratio. Okay, now another related terminology is called the frequency modulation ratio. This is represented by MF, and this is the ratio of the frequency of the triangular wave termed as the switching frequency to the ratio of the sinusoidal signal or the signal which we want to have at the output. Okay, so if you take a note, so basically these two terminologies are like the relationship of the frequencies and the relationship of the amplitudes is opposite to each other. Here we have a ratio of switching frequency, which is the frequency of the triangular wave. Okay, and here we have the frequency related to this control signal, which was a sinusoidal signal, while in case of this particular term, that is amplitude modulation, we had the ratio of peak value of the control signal. Okay, and here we have the peak value of the triangular signal. So this is just for clarification, or in order to remember it more correctly, that in each of these cases we do not have the same terms in the numerator, the terms related to the same variables. Okay, now let us see that how does this comparison or this switching works. How is it established that for what particular case which of the switches will be on and the other will be off, and so on. We'll draw a rough figure of the triangular wave over here. Okay, will not be very clean, but anyways we'll get some idea. This is the triangular waveform, okay, that we have, and then we also have sinusoidal waveform and so on. Okay, this is the control signal. Okay, so the conditions that are being used to determine that at what particular interval or time which of the switches will be on, that is such that the time duration in which the control signal has a magnitude greater than the triangular signal. So that means that the switch in the first switch in the inverter leg will be on, okay, and the other one will be off. Okay, and we'll see in a while that will result in the value of output voltage. Okay, if you remember, we had labeled some particular points as A and O, so it is basically the potential difference across those 2 points. Okay, that would be equal to VD by 2, and when the situation is opposite to this one, that is when V control is less than V triangular, that is the peak amplitude or the amplitude of the control signal is less than the triangular signal, so then this TA will be off, or you can say that the other switch will be, sorry, this one will be on. And in this particular case, the value of the output signal will be minus VD by 2. You have already seen that how does this voltage become positive and negative, but this is how the PWM theory behind that works to make it look like this. Okay, so we just have a comparison over here, so we can see that up till this point, okay, we can see that the control signal is greater than the triangular wave. So in this particular case, the first switch TA plus will be on and output voltage will be plus VD, while for this interval here we can see this one. Okay, since in this particular case we can see that we control, this is our control signal, this one, okay, shown by this arrow, okay, is less than the triangular signal. So for this particular case, the other switch will be on, and that will result in the value to be minus VD by 2. This is plus VD by 2 and this one is minus VD by 2. Okay, this is what we will have for the output voltage signal, that is this is basically the output voltage signal VA naught. Okay, okay, so this PWM scheme is made to work in such a way that the two switches are never on simultaneously. Okay, because that will result in a state which is described as a shoot-through state that effectively short circuits the input voltage across the output, so that is undesirable. And in the same way, these two switches are never turned off simultaneously, so the output voltage will always be switching. This is the graph for the output voltage. It will be switching between these two magnitudes, that is VD by 2 and minus VD by 2. Okay, This will be the pattern of the output voltage. Now let us see it more clearly in the book. So here this is how is it happening. Okay, the same conditions that I just described for the particular case. When the control signal is greater than the triangular wave, here they have shown it for this particular duration. You can see that the control signal is greater than this triangular wave for these two dotted lines. Okay, so you can see that the output is equal to plus Vd by 2. Here you can see the corresponding magnitude, and for this brief interval, for this very short time, you can see that V control is less than the triangular wave. Okay, so you can see that the output voltage is equal to minus Vd by 2, and these are the switching states or the states of the switch. Okay, this is just a representation of the frequency. Okay, that is the switching frequency. So you can see that this is you can see this is also visible over here, that depending on this value the switching takes place. Okay, now let us see its plot or its harmonic spectrum as well, that we can see over here in this figure. This has been plotted for some arbitrary values of the amplitude modulation ratio and the frequency modulation ratio, the two variables that we had described, MA and MF. The frequency modulation ratio has been chosen to be 15, and the amplitude modulation ratio has been chosen to be 0.8. Okay, we can have any different value or like any practical value from a particular case as well, but for our discussion, for our understanding, it does not matter that what values we choose. Yes, for the case of amplitude modulation ratio, the discussion that we are having over here, we have restricted ourselves for to have its value to be less than 1. Okay, as we progress ahead, so you'll see that what is the reason for that. Okay, one reason for it to have be less than 1, because we had said that this is the ratio of the peak value of the control signal to the peak value of the triangular signal. Okay, so that means that if this value is less than 1, so it means that over here what we will have is that this signal over here, that if the control signal's peak amplitude is less than the triangular wave, so it means that the ratio will have an output which will be less than 1. Okay, and this is how we have obtained this curve or this output. Okay, this output voltage represented by V and naught. Okay, but if it exceeds the value of 1, so it means that for some brief time or some brief interval, this V control will always be like above the peak amplitude, and that will have a slightly different output as compared to what we have over here. We'll also see that example going ahead. Okay, but for now we will restrict ourselves that the peak value of the control signal, the sinusoidal voltage, is always less than the peak value of the triangular waveform. Okay, before this having discussion about this frequency spectrum, let us focus on this square wave. Now this square wave which is switching between Vd by 2 and minus Vd by 2 is the actual output voltage of this inverter. Okay, but then if we apply some particular filtering technique, so this dashed line which exactly remembers this carrier wave, and as we had mentioned that this is what we want to have at the output, this is what our desired signal is. Okay, so if you want to get this at the output, so for that we have like visualized this dashed line to be the fundamental component of this output voltage, and we are assuming that this can be achieved with the help of some proper filtering. Okay, and over here this has been labeled as the fundamental component of this particular you can say sort of switching square wave. Okay, and we can also see that present over here at this point in this harmonic spectrum of it. But as we had mentioned that not only it will have some not only it will have its fundamental component, but also there will be some harmonics and their side bands, as we can see over here present. And for more clear idea about how we can plot this spectrum, it is recommended to revisit the basics of the Fourier series, and that will make it more clear. Okay, and that what do we have over here. Okay, now from this plot we can have some important discussion. Okay, One more thing that you need to take notice of, that these all these magnitudes are normalized by a factor of VD by 2. By normalization, we mean that all these values have been divided by this term VD by 2. Okay, so from this we can see that the peak amplitude of this fundamental frequency component, okay, that for the remainder of the discussion will be represented by this particular variable, that is okay. As in the previous curves, you might have observed or noticed that the output voltage was represented by this variable, that is VA naught, okay, and this one basically represents the fundamental component, okay, and this hat sign over here will represent the peak amplitude. I'm writing it over here so that it is more clear to you. Okay, so basically the peak amplitude of the fundamental frequency component is equal to the amplitude modulation ratio, that is equal to MA times the voltage across the voltage value that is available across one of the capacitors. Okay, or if we substitute the exact equation, that is for MA, we can write it to be times VD by 2, but in this case we need to have this condition that V control is less than triangular, as I had mentioned that the graph that we have drawn, in that we have chosen MA to be equal to 0.8, because if it is greater then we can have a slightly different scenario. So now basically this relationship or this equation shows us what we had discussed in the beginning of this discussion about pulse width modulation, and also in one of the last lectures in which we had these three categories of voltage source inverters, that we can control the magnitude as well as the frequency of the output signal. So here we can see that as this is the magnitude of the output and the peak amplitude of the fundamental frequency component, okay, so by controlling like the ratio of these two, okay, in turn determines the control or the value of the output voltage. That for example, if we cannot control this term, that is the input voltage, but it is possible to control either the control or the triangular waveform, and the ratio of these two with the product of the source voltage can help us get the desired value of the output voltage. Now let us see about the other term, that is the frequency of the output signal. Okay, as we had mentioned that the shape or the frequency of the output signal is basically dependent on the control signal. That is, we had chosen a sinusoidal wave to be a control signal, as we can see over here in this figure, and we have desired that we want to have this signal in the output, or we want to have a frequency of this much for the output signal. Okay, so if we want to write our control signal more appropriately, we can write it in this form, that is like we control I hope that it is clear. Okay, this is of course the amplitude. This is how we normally write a sinusoidal signal. This is the peak amplitude. We have already established this, that is hat sign means the peak or the maximum value, and sine omega 1t, that the signal will have frequency equal to omega 1 in radians, or in terms of frequency we can say in terms of hertz we can say it will be equal to this particular term. Okay, and we already have established that this particular case, the V control is going to be less than V triangular, that it is the peak value of the control or the sinusoidal signal is going to be less than the peak value of the triangular signal. Okay, we'll see that case in which we have this value greater than the triangular waveform. Okay, now if we substitute this value of V control into this equation that we have over here, this, if you remember, we had for this particular case, I'll just rub half of the things written over here to make it more clear. Okay, let me rewrite these two equations. That is, I will rewrite this one again, that is the peak amplitude of the fundamental frequency of the output voltage is equal to keep in mind that for all these cases we had this V control less than V triangular. Okay, and in this equation we have also come to know that this V control or the carrier signal is in fact, that is just the representation of it. And again, this one is over there for this particular case as well. Okay, so if we substitute this value into this equation, so what do we get? That is for the fundamental frequency component of the output voltage. Okay, we will have this substitution. We had written omega 1 over here, so continue with that. The denominator is remain as it is, triangular, and over here we had VD by 2. Now we know that these two, the ratio of these two is equal to amplitude modulation ratio, as we can see over here. Rest of the terms will remain as it is. So I just made a mistake over here, that this term peak amplitude of the fundamental frequency of the output voltage, okay, which is represented by VA0, that is equal to this term, okay, the average output voltage, and we don't have this hat sign over here in all of these. Okay, well, for the final equation that we will have for the peak amplitude of the fundamental frequency of the output voltage, we now will have this term V with the hat sign. Okay, for that this fundamental frequency component, this term will be equal to 1, and that will be left with this particular term. So the point of interest over here was to determine that how we can achieve the output frequency or the output signal, output voltage signal to be of the same frequency as that of this control signal's frequency. So here from this equation we can see that it will vary according to the frequency of this control signal. Okay, and since here we have a sinusoidal function, okay, so that is why we'll have an output signal which will be of sinusoidal shape, and the frequency of that will be depending on the frequency of this control signal. Okay, and in all these cases keep in mind that we have this MA equal to less than 1, or we can say that the peak amplitude of the control signal is less than the peak value of the triangular signal. Now let's have some discussion about the selection of the amplitude modulation ratio. Let me rewrite these terms. That is MA and frequency modulation ratio. That is MF. Okay, that what could be the optimal values for example, frequency modulation ratios, like the example or the figures that we saw, in that we had MA equal to 0.8 and the frequency modulation ratio was equal to 15. Okay, theoretically, in order to have easier filtering or the removal of harmonics from the output signal, okay, it is a lot easier to do it at higher switching frequencies. Okay, so therefore it is desirable to have as high a switching frequency as possible. Okay, but the drawback of that is that higher the switching frequency, higher will be the switching losses in the inverter. Okay, so it means that the losses are the switching losses in fact are proportional to the switching frequency. So if we increase the switching frequency, that will result in the increase in switching losses. But at the same time, if we have a higher switching frequency, that means that we'll have easier, you can say, filtering of harmonics. Okay, so basically we have to like have some sort of optimization between these two parameters. Okay, that if you want to increase the switching frequency beyond a certain limit, so you also have to take into consideration the switching losses. Okay, in that particular case. So in most of the applications, as discussed in the book as well, the switching frequency is selected between you can say it is either selected to be less than 6 kilohertz, or it is selected to be beyond 20 kilohertz. What is the reason for it? The reason for it is to have a switching frequency that is higher than the audible range. Okay, so that we don't have a lot of noise in this because of a switching frequency lower than this value. Also that if during the design of a particular inverter, if the optimum switching frequency comes out to be like in between this range, which we do not prefer because of the audible noise, so in that particular case we intentionally increase the value of switching frequency up to 20 kilohertz. Okay, so although there would be some switching losses, but there would be no audible noise in that particular case. Okay, so for example, in a certain AC motor drive application where the output frequency is required to be for example to be like close to around 200 hertz, and in that particular case if we have the switching frequency equal to let us say up to 2000 kilohertz sorry 2000 hertz, so in this particular case we can have this frequency modulation ratio close to 10 or something. Okay, this can be this number, like this is an example of a value of frequency modulation ratio to be relatively small, while on the other hand, if we have for the same particular case, if we have you can say the frequency of the triangular wave or the switching frequency close to, for example, 20 kilohertz. Okay, so that can result in a value of frequency modulation ratio equal to 100 or something. Okay, because it is the ratio of the frequency of the triangular wave or the switching frequency to the frequency of the desired signal at the output, and that will result in the value of frequency modulation ratio of close to 100. Okay, okay, so now also let's talk about a bit about the amplitude modulation ratio, that is MA, which is basically the ratio of the peak value of the control signal. Okay, to the peak value of the triangular wave, okay, termed as amplitude modulation ratio. And as I had mentioned in the discussion that we already have, in that we had mentioned MA to be less than 1, or the case was that V control was always considered to be less than the triangular wave. The peak value of the control signal was also always considered to be less than the peak of the triangular wave, okay. This is called the linear region of operation for a particular invert. So in that we had seen in the waveform for the harmonics that the amplitude of the fundamental frequency voltage varied linearly with the amplitude modulation ratio, okay. We also have this equation which describes the value of the peak value of the fundamental frequency component of the output voltage. This is actually the fundamental frequency component of the output voltage, that is equal to amplitude modulation ratio and a product of the source voltage across one of the capacitors, okay. This was the case when M is less than 1, as I have described it over here. So this also has an advantage, but at the same time this also does have a disadvantage as well, okay. The advantage is that the amplitude modulation ratio being less than 1, it pushes the harmonics into a very high frequency range around the switching frequency, and also in the case of it multiples, so that makes the filtering relatively easier. The discussion that we are having now, that is mentioned in the book by the name of overmodulation. So if you want to read the relevant material, so you can read it from over there. This is 8-2-1-3, okay. This is the topic name that we are discussing right now, okay. So this is one of the advantages, okay. But the drawbacks is that the maximum available amplitude of the fundamental frequency component of the output voltage is not very high, okay. So for example, as we had seen, if this MA is equal to 0.8, okay, so we'll have to take some product of 0.8 with the source voltage, and that will be the maximum available amplitude of the fundamental frequency component, okay. Now, if the requirement is such that we need to have a higher value of the fundamental frequency component of the output voltage, so for that it is necessary to push the value of amplitude modulation ratio beyond 1. In that case, we need to have this value greater than 1, and this is what we have labeled over here, that is called overmodulation. This value greater than 1 is termed as overmodulation. So that means that for some brief interval, the peak value of the control signal, that is of the sinusoidal wave, will be greater than the other wave that we are comparing it with, that is the triangular wave, okay. The disadvantage in this particular case is that now the output voltage will have much higher values and higher number of the harmonics, okay, as compared to this particular case when the value of amplitude modulation ratio is less than 1, okay. Another thing here, that in this particular case, okay, the value of the output, the amplitude of the fundamental frequency component of the output voltage had a linear relationship, okay. Now that equation is no more valid, this equation is not valid anymore, and this relationship is not linear anymore, okay. You can see a graph of this representation, okay, which will show us the relationship between the linear, or the value of amplitude modulation ratio to be less than 1 and greater than 1. And now this is the waveform which shows a relationship between the amplitude modulation ratio, as we can see over here on the horizontal axis, while the same parameter that we had seen before, the normalized value of the fundamental frequency component of the output voltage, okay, Here we can see that previously, as we had described, that in this particular range where amplitude modulation ratio MA is less than 1, so in that case there is almost a linear relationship, and we used to see that there we used to take the product of amplitude modulation ratio with this VD by 2 factor to determine the value of the peak value of the fundamental frequency component of the output voltage. But beyond this particular range, as we can see over here, the relationship is no more linear, and we can see that it may have different values at different points. Okay, and after reaching a very high value of amplitude modulation ratio, as we can see over here, approximately 3.24, okay, this turns out to be a square wave representation, okay, at the output. Okay, so basically from pulse width modulated waveform, now it turns out to be a square wave switching representation for a very large value of MA. Well, for the rest of the values, we will have this relationship, that is, it will be equal to this is the fundamental frequency component of the output voltage. This relationship is valid in the range where we have this amplitude modulation ratio greater than 1. For less than 1, it was a linear relationship or a linear function of this particular parameter, but beyond this, as we can see over here, that once it reaches this point, it becomes equal to VD by 2, okay, it's product of 1, and beyond this, then we can see it can reach to a maximum value of this 4 by pi into VD by 2, okay, or that can also be written as, this particular term can also be written as 1.273, and we have just seen it over there. Now let us discuss a little bit about the square wave switching. So you have already seen this in the last PowerPoint based recorded lecture, but now let us see it from the perspective of this amplitude modulation ratio. And in this context, the definitions that we have discussed up till now, that in this particular scheme, each switch of the inverter leg that we had represented earlier is turned on for 180 degrees, okay, like for half of the time of the desired output frequency. So whatever is the output desired frequency, for 180 degrees of that, one switch will be turned on, okay, and the other one will be kept off, and so on, okay. So it will have an output representation of something like this, okay. This is our output voltage. So this is that complete time period or complete cycle, okay, of the fundamental frequency component, and in this time duration, this is equal to VD by 2, while for this particular case this is equal to minus VD by 2, okay. So in this particular case, what happens that this value amplitude modulation ratio is made so large that, for example, if we have this triangular wave, okay, so the value of sinusoidal signal is made so large that it is, for example, for this entire range, we can see that the value of this is our control signal, and this is our triangular signal, So as we had a condition that as long as the control signal is greater than the triangular signal, so for this whole region this is greater than this, and our first switch that we had labeled as TA plus will be on, while for this particular range we can see that the value of the control signal is less than the triangular signal. So the other switch, that is TA minus, will be on, and when TA plus is on, we have the output voltage equal to VD by 2, and when the other TA minus is on, the output voltage is equal to minus VD by 2. So this is how we'll have this representation, and as we had mentioned that the frequency of the output signal, the desired frequency will be the same as that of this carrier signal. So basically we can see over here that it is having the same frequency of this one. Okay. In the previous cases there was some relationship, or there was some connection of the amplitude modulation ratio, that is MA of the output voltage into VD by 2, that was equal for this fundamental component of the output voltage. But here beyond this range, when MA is much greater than 1, so this is no more valid, and we can see that the peak amplitude has a fixed value in this case, and it becomes independent when it is operating in the square wave region. And we had seen over here that this is the square wave region of operation, and it has a fixed value. How does it become a fixed value? We'll derive that relationship also. The only advantage that we can see of like this square wave operation is that each of the switch changes only once, like it changes its state only once every half cycle. Okay. So at very high power levels, when we are having solid state switches which may have very slow turn on and turn off characteristics, so this can only be seen as the advantage of this one. Okay. The disadvantage is that in this particular case the inverter or the square wave switching scheme is not at all capable of regulating the output voltage magnitude, because now it becomes independent of the relationship between the control and the triangular waveforms. Okay. So this is, we had also discussed when we had discussed this category of the voltage source inverters, that in this particular case the inverter will not be able to regulate the value of the output voltage, the magnitude of the output voltage. So for this it is necessary that we need to regulate the source, regulate the input voltage, input DC voltage. So because now it depends completely on the value of VD by 2 in both of these magnitudes, so we need to regulate that particular voltage to have the desired value at the output. So I hope that this discussion would have given you some idea. In the last one we had directly discussed the half bridge and the full bridge inverter circuits, okay, without paying a lot of attention to the relevant terminologies and basic concepts. So I hope that this would have added quite a lot related to the concepts and the terminologies of the inverter circuits. In the next time we will revisit the half bridge and the full bridge inverter topologies in context to the discussion that we have had for this particular case.